All right, good morning. So this week will be the second last week, and then we got one more week next week, and then done. Well, of course, you still got the exam. So let's see where we are. Just make sure you don't really fall behind for the final 2 weeks, which will be also quite important for your learning. Don't forget, there's a bonus opportunity as announced yesterday, course evaluation, completely anonymous. It's official. So let me show to you. You can definitely find a link in the announcement I made, but so far it's not too bad. You can see we now got this, more than 10%. All right, so it's your right. If you want to do it, feel free to do it, and you might just get a bonus at the end. If you really don't want to do it, that's okay, right? But I believe after submitting your grades sometime in late April, they will open the comments for me to look at after the everything's done. So I definitely wouldn't know the result before the actual submission of the grades, so you don't need to worry anything about it. Anyway, it's something for you to think about. Yes, Adrian.
Why are we being asked to do the course evaluation early? Because if I could do it later in the period, like April 10th or 11th, then I have the opportunity to consider Lab 4 and programming test 2.
You know, it's completely up to you. I'm not forcing anybody to do in the early participation, because from my experience, usually students get so occupied by many other things. So I would just prefer to really get everything, done in that early participation. But if you really prefer to do it after considering Lab 4, that's no problem. Yeah, it's only another bonus opportunity for everybody. So if we can reach that response rate, that's awesome. I'll be happy to give everybody bonus. If we cannot really reach it, I will still see your comments, and that can also help myself improve. So please don't feel pressure to really do it whenever you see my reminder. Okay, don't get it wrong. Okay, so about programming test 1. If you want to go over the submission that you made, because we don't really distribute the solution and your answer back for the programming test, because that was done in the lab test mode. But you're more than welcome to reach out to either myself during my office hour as ever, but if you really want to go over with the TA, that's okay too. What you gotta do is send an email to Andy. And I announced his email actually way earlier, back in the semester, just in case you don't know. Go to the E-class, and then you will see emails of TA, and that's Andy's email. Okay, go there, and then he will set up some time with you over Zoom. So in the first instance, you guys can spend about 10 to 15 minutes going over your answer and to see where you got wrong. And definitely you can get some feedback, and you can definitely improve for your next programming test. Okay. And for your next Thursday, you're going to have your programming test number 2. Okay. I'm going to release the guide very soon, before Thursday's class, the latest. And then after the submission deadline for your lab number 3. That one there has been extended until Friday, noontime, I believe. Okay. So right after the submission deadline on Friday, I'm also going to give you some practice question for programming test 2. But let me give you some idea. For your programming test 2, the format is basically identical to your lab number 3. Meaning that there will be 2 parts. So part number 1, you're going to complete certain context according to the specification. And this part here is very similar to what you did for programming test 1. So that one there should be no surprise. And that's pretty much part 1 you did for your lab number 3. And for part number 2, that one will be the more challenging bit. And that one there is about to complete the manual proof with the rodent. So this is why we try to give you the step-by-step guidance, in the actual instruction. And we are trying to also collect some informal feedback from the TA, and some of you I reach out to. And then I'm going to actually update a slightly updated version right after class today. So actually the instruction is even clearer. But I believe the first draft is already clear enough. But if you really got any trouble understanding the instruction, feel free to reach out. And for today, for your lab number 3. So for today, it's Tuesday. Right? If you go to the lab session, I believe it's 1 p.m. in the prison lab, Maria will be there. Okay, and also for Thursday, that will be 2:30 p.m. I believe. That one there, Andy will be there in person. Just drop by, and then if you got any trouble completing especially part 2, just go there. Okay. Let me just say one more thing about your lab number 3, which is really important. Okay, over here. If you look at the instruction for lab number 3, okay, let's open that. Okay, just notice that submission deadline has been extended until Friday, 12 noon. Okay, I'll give you guys some reminder on Thursday. Just submit it in time. And this one here, basically just make sure you can complete the part 1, which I already gave you solution. Okay, and also for part 2, make sure you can complete a proof tree and make sure you practice as many times as possible. That's definitely going to help you for the programming test next week. As I said, the rodent prover itself is a very complicated monster over there. So it's not really worth our time to really dive too deep into it. That will take the entire course, or 2 courses to complete it. So what I decided to do instead is to have a very particular proof pattern that we're going to learn to get a flavor about what a prover is about. That's all you need to do for this course. Okay? And if you haven't really done part 1, I would suggest before looking at this actual solution, you really want to look at that too. I mean to attempt it. The actual solution to part number 1 is on the appendix. Okay, I'll show you very quickly. And I would suggest, even if you have already attempted, sorry, it's a bit long documents. And then maybe it's still loading. Let me do it again. Okay, there we go. Sorry for the delay. Okay, so you can see that there is some appendix over here. So I would say if you have already attempted your part number 1, take a look at the solution that's already posted. Compare the answer, see if you have any doubts, and reach out to either myself or the TA to even talk about part 1. And then when you actually follow part 2, we assume this particular solution to do the proof. But I believe if you actually got your own solution, you might just be able to also continue with the proof with a similar idea, maybe, but you have to experiment yourself. But this will be rather straightforward based on the description that we put on part 1. Okay. And of course, for part 2, you just gotta do the step-by-step, follow through, and then really see what's going on over there. Okay. Lots of mouse clicks, but I have to know when to click them and when to enter the hypotheses. Okay. Yeah. So any doubts about any step over there, we can clarify, and then if needed, we're gonna have another second revision to really update the instruction anytime. Okay. But it's really important you spend the time and do the work. So guys, any question about your lab number 3 and the programming test number 2 next week in general? Adnan. Mm-hmm. Yeah, that's true. That's true. In the actual programming test, this is still tentative, but most likely the case. I will confirm when I release the guide. And once I release the guide, it's not going to change. What I'm thinking about is we're going to have about 60% of the test mark to be based on part 1, meaning that if you're just able to manage to just complete part 1 and everything's reasonable, you can still get a very decent grade, 60%. And for the part 2, it's really for us to really know whether you really have learned something new about the prover. And that one there, the steps that you have to follow through during the lab test will be very similar to what we gave to you for lab number 3. Okay? So to really get 100%, hopefully everybody will get it, right? We'll see. But the problem we're going to give to you in the actual test will be somehow similar, right? We wouldn't really give you something that will expect a completely different pattern to interact with the prover. That's not our intention. Okay? We just want to make sure you can at least master this particular pattern. So, Adam, hopefully that answered your question. Okay, good. Alrighty. And one more thing to mention, I think that this is just for a little bit later. I think our exam, if you look at the semester calendar, it's not actually very late. So I think as soon as we finish the actual teaching, and We don't have that much time. Well, we have some time, but not that much. Let's take a look. So we are now over here, 28th. You got your programming test 2 next Thursday. That'll be the last one. And we have our last class next Tuesday. Make sure you come. And hopefully I can talk a little bit about the exam, a little bit. Okay. And then I think our exam is going to be on this particular week. I forgot, it's either Saturday or Sunday. Anyway, Sunday? Okay, maybe. Okay, please double check. And then I think what we can do is maybe after the study date, we can try to schedule 1 or 2, maybe Q&A, like over Zoom or maybe in person. So you guys can still ask me questions. Okay, that will be the plan. I'll reach out to you guys about what time might work the best for the majority of you. And then we can go from there. All right, I think that's about what I want to say. All right, guys, any question? Okay, again, please don't get me wrong. This one here is completely up to you when you want to do it. You can choose not to do it. That's okay. Completely up to you. Okay? But if you want to do it and get a bonus, you need to do it early. Okay? It's completely your option. Okay, so today I would like to definitely finish off the first refinements. Once we finish the first refinements, and I'm going to talk about also the second refinements, and all the concept in the second refinements will just be what we talked about in the first refinement. So it's more like a reinforcement about everything that we spoke about before, which is good. Repetition is always nice. And for today, we're going to talk about, number 1, divergence, and number 2, relative deadlock freedom. These 2 ideas. So these are the final 2 ideas to finish off about the first refinement. Okay? Let's see how long it will take. And as always, let's do a very quick recap about what we said last time. Okay, give me one moment. Oh, okay, over here. Okay, so this is where we were last time. And last time we talked about invariant establishment in a refinement. That one is just the same idea. And then we talk about, this is really important, conceptual map you want to have. And once we get another refinement called M2, we're going to have similar idea. We still got the abstract events and also all the concrete events, which can be subdivided into either old or new, the same. Okay? But for our purpose for M1, just remember MLL, MLN, they are the abstract events, which has the very explicit counterparts in the abstract model. And for the new events, ILN, ILL. And the most important result that we went over last time was to see these 2 and all the new events in general should correspond to an event in the abstract called skip, which does nothing. Okay? So the formal way to say this, which is also on the slides, every new event is simulated by the skip events in the abstract model. Right? Just make sure you review that point in the slides. Okay? And we talk about the guards and action for the new events, and we talk about how to figure out tracing. And we need this kind of tracing ability very badly today when we talk about how we can measure the possibility of divergence. Right? That's a very important idea before we can take a break. Okay? We'll get there. And we talk about the skip events over here to see how some ILN, new events, will correspond to the skip. Right? That's what we said last time. And then we talk about how you can prove about invariance, which will be the same as before. And exercises for you guys. And this is basically where we were. Right? I would suggest, only for this part, maybe I wouldn't repeat again. So if you got any doubts, you can check the recording. This part here talks about, given any model that you might be given maybe in the exam. If I say, if for a model, I can show that it's provably correct, meaning that I can prove every event can preserve the invariance. Can I really conclude it's really a good model? It turns out not necessarily. Because if your invariance simply include things about the types of the variable, it's not enough. It's underspecified, so-called. Right? You can find out more details about what I wrote over here from last time. And what I want to continue and from scratch will be talk about divergence. It's a very important concept to know. All right, so that's where we will start. Okay, over here. Okay, let's now take a look at this model. The invariance over here is very, very weak in the sense that it's not difficult not to violate it. we simply say A, B, and C are just integer, meaning that they can be negative if we want to. Again, it's a very artificial, contrived model just to illustrate about divergence. Let's take a look. What I want you guys to consider is the following trace. Let's now talk about a concrete world. So let's say here. So let's say concrete transitions. And not worry too much about whether it really make real sense. Let's just see if that would be allowed by the model. At the moment, you can see these two events are guardless, always enabled. Okay, just to illustrate the point. And of course, back in your written test number 2 coverage, when we talk about M0, and we did have our MLN being guardless in the beginning, and that is actually not. So in general, if you got any event that's guardless, it's not a good thing for you to have. You definitely want to fix that in one way or the other. Okay, so let's say we have the following trace. We initialize the model. And then, is ILM enabled at this point? Indeed, because it's guardless, right? Its guard is always enabled. So what I will do is I'm going to say IL in. And then after that, I'm going to say IL out. Basically, what I want to do is think about this is the island. This is the breach. What I want to do is I want to do IL in, IL out. IL in, IL out. IL in, I'll keep doing it. It's allowed by the model. So nothing wrong as far as the model definition is concerned. So let me do a little bit more. IL in, and then IL out. Okay, you can see you can go indefinitely. And this is the trace I showed to you right before we finished the class last week. And let's look a little bit more deeper into it. What's happening over here is, if you look at this part over here, the way to understand this pattern over here is, number one, the new events interleave indefinitely, which means it might just still go forever. Right? You can see over here we got IL in and IL out only. And these are the new events. And these two are the old events. Let's remind ourselves. You can see here, these two, this one here, and this one here. So these are the old events. And these two are the new events. Okay. Apparently, having this is not good. Why? Because you're basically, there's no card on the breach. And somehow you're just able to do IL in, IL out, IL in, IL out. You never allowed any card to really go back to the breach again, which is ML out. We're preventing it from happening. So in this case, out no longer possible in this particular scenario. Okay? I'll write it down, and then we'll see from another angle. So what you want to understand is, number 2, for this one here, none of the old events is allowed to occur, right? Because these new events just keep happening, all right? This is bad. Whenever you got any refinement model where there is a way to interleave just the new events indefinitely, which will prevent any of the old events from happening, that is something called divergence. Okay? So this is something called divergence. And another term for that is called Livelock. And I want to compare this term to deadlock right away. Right? If you guys recall, deadlock simply means no events can occur. Livelock means some events can occur, but somehow they actually got into some infinite loop of occurring. In this case, we got some infinite loop between IO in, IO out. They simply keep occurring infinitely. In that case, you can still not do anything useful. So both deadlock and lifelock are two extremes that you want to avoid. Yes?
Are the cases where something like Livelock can happen? Is it bad, or is it always bad that
Livelock is always bad, because that means you have certain very small set of events that can simply keep occurring. That'll prevent other events from happening.
Okay.
It's always bad.
Yeah.
On the other hand, let me just follow up a little bit. What about deadlock? It's I would say, depending on the application domain, if you have a system, deadlock is definitely bad. That means your system will stop reacting to the outside world. On the other hand, if you talk about other domains, deadlock is not necessarily bad. For example, if you talk about a sorting algorithm, it's like a sequential domain. Get into some terminating states where the result is available.
Right.
Okay? Yeah, anyway, just some aside. Okay, it's called lifelock, and over here, you want to think about, that means a set of events keep interleaving. Okay, that's a little bit incomplete, but you can see the definition in the slides. Let's take a look, and then I'll see one more thing about the divergence. And then we can see how we can somehow prevent it, and then there will be a solution to it. All right, so that's the model we talk about. And that's the trace that we just talked about over here. Okay, and then, okay, so let's now talk about one more thing. Another way to see how bad this is to see how this can be simulated by the corresponding abstract model. Remember we said every event should really have its corresponding abstract counterpart. In the case of new events, it would just be skip. Okay, let's take a look. And if you got the abstract transition, and in this case, init is just init, the abstract version. And ION will just be a skip. IOL will just be a skip. And then ION will just be a skip. IOL again will just be a skip. So you keep skipping without MLL, MLN ever can occur. Now you can see even clearly that is really bad. Okay? So if you look at the abstract world, it's as if you have some, let's say in the C language, you say while maybe 1 or true. And then you simply do nothing. Just keep wasting the resources of your computer. And then nothing can be done. Okay? So guys, quick recap, and then we'll go back to the slide to finish off. When you are given a model, especially refinement model, you want to pay attention to how the design has been like for the new events, because there is a phenomenon which is bad always. That's related to the new events only. In that case, it is possible to have an indefinite trace where you just got interleaving between new events, meaning that the old events can never get to happen again. In that case, it will be as if you're doing skip always in the abstract counterpart. In that way, it's completely bad. Okay, Ryan. You know, for Livelock, for the old event, that's okay. Because if you think about what's happening here, that's a good question. So Ryan's question was, here we talk about an infinite interleaving of the new events. That one there simply corresponds to skip, 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 skip. That's like a BC loop. And we agree that that one's bad. Another scenario, what if, okay, let me just, so here is the question. Is an infinite interleaving of old events bad? Not necessarily. So that's why we wouldn't consider it as a Livelock. For example, let's say we got init maybe you got ML out, just indefinitely. Let's say the capacity will allow it, so that's why it can keep occurring, right? in this case, let's say this is a concrete version. Now, if you look at the abstract version, are we going to have anything like a BC waiting, like a while true loop? Not really, because over here, we just got init and followed by not skip anymore. It will just be ML out, and then ML out, and then etc. So that's okay. So having infinite interleaving of the old events is not a problem because it still corresponds to something useful in the abstract world. On the other hand, if you got infinite interleaving of the new events in the concrete world, it will simply correspond to keep doing skip, which is like this. So that's not good. Yeah, go ahead, follow up.
The model isn't correct. Go into negative covers. So in that case, could there be a Livelock due to a faulty abstract?
It's a very good question. So you're basically still talking about, let's say, given a slightly different model, how do we tell if there's a possibility of a Livelock? I would say in general, if you don't really have a systematic method, like a proof obligation to check it, it would be difficult. Because you simply have to figure out if there's any interleaving trace and to show that divergence is possible. But what we're going to show you after this illustration here is to see two proof obligations about your model. That one, those can easily tell if you can run into divergence. That's something we'll see. Yeah, Nathan.
Is the issue that you can't have an interleaving, or that you can't have an interleaving which locks which makes it
Yeah, so yeah, yeah.
That you can get out of that.
Yeah, so you definitely want to avoid running into some infinite leaving of the new events, in which case no old events can really ever happen again. You want to avoid it. But to really avoid it, you will need some extra mathematical concept to help you with that. That's something we're going to talk about.
But is the issue that you get into a state which blocks all the old events, or just that they have new events?
It's not really just about particular states. For deadlock, you run into a particular state from which no events can occur anymore. That's deadlock, right? For Livelock, it's not just about particular states. For example, here, you can see starting from here, we can just keep doing new events without the old events can ever happen again. So not just about the single states. It's just about the system design, which will allow the events to really happen indefinitely. Right? Okay, I'll leave you there just for now. Hopefully things will get a little bit more clearly later. All right, guys, any question about seeing the correspondence of the new events and the BC waiting? That's the main thing I would like you to get an intuition about before we get to something that's very mathematical. Okay, and divergence and Livelock as well. Okay. Yeah, so I think these two bullet points also summarize about what the difference is between Livelock and deadlock. And for example, if in the exam I ask you to really explain the difference between Livelock versus deadlock, you should know how to do it, right? Anyway, I'll leave that to you. Okay, let's now move on to talk about, now that we have some intuition about how the Livelock can actually occur. Again, you just got an infinite interleaving of the new events, which will prevent any old events from happening. That's Livelock. Now, given an abstract, like an arbitrary refinement model, how can we tell if a Livelock is ever possible? That's something we'd like to see. And the idea is we want to talk about a new concept. So far, we talk about something called invariance. So that is something you want to make sure is always true, right? And you want to make sure it's maintained. And we need another concept. It's called variance. Okay, that's something completely new to you. I want to maybe make some very quick clarification.
Yeah.
Okay, over here. So far, we talk about invariance. think about invariant is like an expression that should always hold true. Okay, that's invariant. That's something you know pretty well. What about variance? It's also another expression. An expression that, let me say a little bit more, should always hold true after each event occurrence. Right? That's why we have to prove invariant preservation for every event. Okay? Now, what about variance? Expression that should how about not should? That may change. You will see exactly how this can be the case. That may change after events occurrence. Okay, and then let's now get a bit more information there. I just sketch, right? Because the mathematical concept there is a little bit heavy. So I want to make sure you understand this one first. Invariance is a Boolean expression. Variance is an integer expression. Okay, I want to draw two diagrams over here to plot the invariant versus variant over time as we take more and more events. Okay, let's start with invariance. Let's say this is the invariance. Let's say, for example, this means it is true. This means it is false. Right? And let's say, for example, let's say after the init, invariant should be true. After another event, doesn't matter if that's old or doesn't matter if it's old or new. For example, ml out. And then let me just use the M0, MLN. Invariant should always remain true, right? So it should be a flat line, like that. You may haven't thought about it, but now is the time to program that into your head, okay? Invariant basically should always be true. That's why it doesn't change. That's why it's called invariance. What are variants? That one's interesting. We are still going to plot in a similar way. Let's say here, and when we talk about variance, okay, and then because it's an integer, and to be more precise, it's a natural number, as we'll see, okay? And for invariance, we know that it's a Boolean, right? Okay. And think about we have the horizontal axis is going to be about occurrences of the events, okay? So it could be, for example, let me just give you one example right away, and we'll look at that particular example in much more detail in a moment. Okay, I'll just write it down. Okay. Let's say you have some init, and then you have ml out, and then you have il in, and then you have il out, and then you have ml in. Right? It's totally sensible. Okay? And let's now be more careful about the category they belong to. This one here and this one here, they are old events. And this one here and this one here, they are the new events. Okay? And the precise value, don't worry too much about it. We're going to see how to really plot their value later. The actual curve you're going to see is something like this. After init, it might just be 0. Okay? After ML, for example, it might be some value that's not 0. After every event occurrence of the new events, you're going to strictly decrease the value of the variance. Okay, and then when you get to the O events over here, it's going to stay 0 over here. And then somehow, by regulating the new events using the variant, we can actually see, is it possible for, since we know every new event is going to strictly decrease the value for the variance, can we ever get below 0? We shouldn't. If we are if we are ever able to get below 0 for the variant value, that means our system model is not correct. Okay, that's some proof obligation we have to show. But what you want to remember is the curve. This is not exactly precise. I do apologize, but we'll see some very precise one once we talk about the variant definition. The idea will be, whenever you got any, you have to start with something, and then that's actually strictly positive. After the occurrence of every new event, it's going to decrease its value. And then once you get to 0, for example, it's guaranteed the new event is no longer available. In that case, you can resolve the infinite interleaving problem because it's bounded somehow. And you have to really have some occurrence of the O events before you can actually get a variance back to positive, and then you can try again for the new events. It's a very kind of vague sketch, but it's not too bad. Okay, just for now. Okay, you will see a much more precise diagram a little bit later. Okay, but understand about these two conceptually. That's really important. So what I would like to do now is write some slides, and then we'll do that example right away. Okay, so this is the variance that we are doing, and the variance belongs to the entire system. And a variance is going to be defined in terms of any constant. Remember C, right? C is a constant. And also W is a concrete variable, right? You can use any combination of these terms to define. And concrete variables, okay? Okay, so now let's take it for granted. Let's consider this variant here. 2 times A plus B. Okay, we know what A is. We know what B is. And now we want to say every time we're going to evaluate this particular variance value, 2 times A plus B, after an event has occurred. That's what we're going to do. And then we're going to plot the variance value, like what we did earlier. And we're going to see exactly what's going to happen. Once we see that plot, we can extrapolate about a 2 proof obligation of invariance. Okay, that's what we'll do. Let's now do that. Okay, and let's now try. Okay, we got variables A, B, C. So talk about M1. And we got all the invariants, which you're familiar with. We got O events. Okay, these are the O events. And these two are the new events. Okay. And what we want to do is to see this particular trace. Okay, we got Emma out, Emma out. Well, let's see exactly what this is saying. So if you remember, let's say this is the island, and that's the bridge, and that's the mainland, right? Emma out, so we got 2 cards. ILN, ILN. So these 2 cards move to the island. IL out. So these 2 cards also move back to the bridge. And then MLN, MLN, they go back to the mainland. Okay, that's the trace we're talking about. Enough for us to see. And let's assume this is the variance. Okay, we're going to do this plot once we are done with the tracing. After every event, starting from initialization, we're going to figure out the value for A, B, and C. And then we're going to evaluate, let's say we finish this tracing first. And then we're going to evaluate the V, which is a variant expression, and see how that would change. Okay? It's very important for us to do that. Okay, let's try. Let me start with, after initialization, A, B, and C will just be 0. Right? That one's easy. 0, 0, 0. What about after ML out? That one there is going to just increment A by 1. So that means 1, 0, 0. Okay, and then another ML out is going to be 2, 0, 0. What about ILN? ILN is going to decrement A and increment B because that car on the bridge is going into the island, right? So that means 2 will be decremented to 1, B will be incremented to 1, 0. All right, another car from the bridge going into the island. So that means A is further decremented to 0, B is further incremented to 2. So now we got 2 cars in the island, okay? Let's say one car wants to go back. So they'll go onto the bridge. So that means 0, 1, 1. You can see there's one car heading back to the mainland on the bridge. And then we got another aisle out, 0, 0, 2. Okay? And question for you. Question, very important question. After this particular states, okay, I'll put it here. Is it still possible to have an occurrence of new events? Is it possible or not? So you want to look at this states, 0, 0, 2. Can we do ILN from 0, 0, 2? Not really. A must be larger than 0, which is not. Can we do IL out? Also, we cannot, because it must be B larger than 0, but B is 0. So that means at this point over here, we are not able to have any more interleaving of the new events anymore. So it cannot be indefinite. In order for us to really enable any of the new events again, some old events must happen. So this essentially breaks the possibility of divergence, right? So here, I want to write some comments over here. Occurrences of old events allowed further occurrences of new events. Okay, that's really important to see. All right, let's now finish off the tracing and then we evaluate the variance. So let's say we have 0, 0, 2, and then what about MLN? After MLN, one of the car is going back to the mainland. So 0, 0, 1, and then 0, 0, 0, and we're back to the original state. Okay? Are we okay so far? We haven't even evaluated variance just yet, but I'm trying to give you more insight into this example here. Okay? Okay, so now the most important thing to do is to evaluate the variance. Okay, let me see if I can move this a little bit to here. Okay, that's possible. Okay, how about here? Okay, let's see, variance. And how do we evaluate the variance? 2 times A plus B. Okay, 2 times A plus B, 0. 2 times A plus B, 2. 2 times A plus B, 4. And 3. Sorry, I didn't write 4 very well. And 2 times A plus B, 2. 2 times A plus B, 1. 2 times A plus B, 0. 2 times A plus B, 0. And then 0. Okay, and there will be some exercise for you. I will mention that. Okay, so guys, make sure you actually understand so far. We just evaluated variance. How did I come up with the variance? That's another story. Just assume. In the exam, I might just give you some variance for you to start with and kind of ask you, is that the appropriate variance? In that case, one way to tell is come up with some trace and then try. All right, let's now try to plot very precisely. So since like we got different values, 0, 2, 4, 3, 2, 1, right? So the variant is going to be 0, and then 1, 2, 3, and 4, right? 1, 2, 3, and 4. Okay? And then let me try to save, just put it here. So we got init. Okay, init, after that is simply just 0. And then we got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'll write them in maybe the short form. ML out, ML out, IL in, IL int, IL out, IL out, ML in, and ML in. Right? 8 events, occurrences. Okay? And we start from 0 here, and then we get to 2. And we get to 4. And we go down to 3. Go down to 3. And go down to 2. Go down to 1. And then remains 0, 0, and 0. Something like that. Okay, so what we have is something like this. Okay, that's pretty much what I try to sketch over here. Pretty much. Okay, anyway, this one is more precise. Okay, just make sure you kind of try to follow what's really going on over here. So far, it's not too heavy, right? Question? Yes, Adnan. 0, 1, 2, 3. Sorry, which one? Sorry.
The last 3 should be 0.
0, absolutely. Yeah, absolutely. Thank you so much. Yeah. Yeah, I definitely see that point. Okay, so after IL out, it will be 1. And then it's going to be 0, 0, 0. Absolutely. Yep. Okay, let's now make some observation. Okay, number 1, over here, you can see we got ML out, ML out. This part over here, let me just try to get a little bit thinner. This part over here is about old events. Old events means the variance increases its value. Usually. Could be increasing or could be stay the same. We'll see another example. And then it's more important to see. For new events over here, for every occurrence, they are actually going to strictly decrease its value, right? So here, for the new events, the variance is actually going to decrease. And then we see another possibility for the old events. Over here, you can see for ML in, right? The last 2. Over here, you actually got the old events. They might simply just maintain the variance to be the same. Okay? One more thing to say. You can see the variant value start with 0, may go as large as possible, and go down, and it never goes below 0. Right? That's also important for our measurement. Okay? So 2 things. Number 1, the fact that the variance is strictly decreasing. Right? You can see this line over here. Number 2, the variance is always larger than or equal to 0. These 2 will be the proof obligation we want to formulate. This really is a benefit because rather than having to come up with the trace ourselves and to plot and then to see the trend, we can simply generalize the observation into 2 proof obligations and then prove them. If we can prove them, that guarantee there's no divergence for your model. If you cannot prove them, or somehow you got an unprovable sequence, that means you may have to fix your model to avoid divergence. All right? So these are the 2 things that's really important. Okay? Number 1, the variance should be strictly decreasing for the new events. Number 2, the variant value should always be larger than or equal to 0, or is a natural number. So these are the 2 proof obligations for variance. Okay. Are we good so far? Okay. It's about 15 minutes already. I think you guys really deserve a break. Why don't we take a short break, take attendance, and then after the break, we can now formulate this observation here. Right? Okay. Okay, let's now take attendance. All right, check in, please. Yeah, we're taking attendance now, so just make sure you check in before I close it. Are we good?
No.
Not yet? Okay, I'll wait. Oh, you want to sign? No problem. There we go. You want to bring a pen? Yeah. Are we good? Okay, I'm going to close it. Yeah, if you want to sign, the paper is on the front. Yeah, guys, take a 2 minutes break, and then we'll come back. Thank you. Can you also put a check mark besides your name? That'll be great. Thank you. Oh, didn't work for you?
Yeah.
Okay. You sorted by last name. It should be the first page, I guess.
I asked before, can I do the program test one, maybe during your office hour again?
Yes, of course.
Without counting the mark, I just want to do it again to make sure I understand how to do it.
Yeah,
and,
for sure.
I can get you right.
Yeah, sure. You want to come today?
I want to come today.
Please come. Yeah.
So I just bring my computer and then can I do it on my computer?
Yes, you can bring your computer. No problem.
So I bring my computer and maybe you can give me the question and then I can do it during the office hour.
I'll be there. Sounds good. Just come and then we'll.
When is your office hour today?
3:30.
3:30?
Okay.
Thank you.
And okay, Sarah.
Sir, I have a question. So I'm kind of concerned about 4315 and want to talk to you. So do I come at your office hours or?
Yeah, office hour.
Yeah?
Yes,
Okay.
please come and then we'll talk about it.
Okay, thank you.
Wallet, question.
Quick question. Is the final exam going to be written or is it going to be on?
It's going to be written,
It's going to be written.
paper.
And is there going to be written there?
No. Let me
the
address that.
sense that-
Let me address that very briefly
Okay.
after the break.
Perfect. Thank you.
All right, guys. Another minutes, and then we'll continue. Okay, we'll start in just one moment. Alrighty, let's start again, please. Okay, I think some of you asked me about the format for the exam. I can chat briefly about it, but I'll definitely give you more detail, slightly more detail on the final week. So for your final exam, okay, exam. Number 1, 3 hours. And I believe it's being scheduled on some exam center. Please double check. I forgot which one it is. And then it's going to be completely paper. No rodent. However, of course, it's a paper test. You cannot use rodent for sure. But you may be asked to read or write in rodent syntax. And of course, since humans are going to grade your exam, if you really make some tiny mistake, we will be tolerant. Oh, good to know. Okay, sure.
And it's Sunday, April 16th in the afternoon.
Sunday, yeah, thank you. Sunday, April 16th. And what time?
Afternoon, which is 2 p.m. to
2 p.m.
5 p.m.
Yeah, make sure you get your lunch before you have the exam. You need energy for that exam. Okay, and then yeah, it's the tennis center. Okay, thank you. Okay, and one more thing. I think this might be good to mention earlier so you can get it prepared. You guys will be allowed to bring data sheets. Okay, good. But there will be some strict policy, which I'll mention right away, right? It's not going to change. Once I mention it, it's not going to change. A piece of data sheets will be allowed. Okay, but number one, only one side. Okay? Okay, number two, it must be computer typed, not handwritten. Okay? And the font size should be larger than or equal to 10. All right. Smaller than that is not good for your eyes anyway during the exam. All right? Don't try that. And if you really ask me what you want to put on the exam, okay, Inference Rule for sure. And then if there's any particular insight you actually want, that's easy for you to forget, you can put some insight there as well. Well, maybe with some common patterns for the guards, for the action, or for invariants. Feel free to put them. That's okay. I wouldn't check the contents, but make sure it's computer typed. So you still got time to get it prepared. So I'm telling you the policy, I'm not going to change it. Okay? Okay, that's it. All right, so I think that'll kind of help you maybe also get prepared. I think preparing some data sheets while you're studying for the exam is beneficial, so you know what to really put. Whether or not you really want to put some sequence proof, it's legal for you to put some sequence proof on the paper. But whether or not it's really worth using the space, I'll leave that option to you. Okay? Okay, good. And then I'll give you a little bit more maybe tips about maybe possibly how you should really study for the exam, etc. Maybe in the final week. But it doesn't hurt for you to start maybe going over the material right away. It definitely wouldn't hurt. Okay, so let's now move on to finish off the variance issue. Right, very quick recap, and then we should at least finish the variance. Relative data freedom wouldn't take that long, so I'm okay to. We feel comfortable to talk about it on Thursday to finish that off. Variance and divergence is the trickiest part, I would say, for the refinement, so we want to get it right. Before the break, we talk about basically, given some arbitrary model, if you're able to have some infinite interleaving of the new events, which will prevent any old events from happening. That's something called Livelock or divergence. And to look at that from the abstract world, it will be corresponding to like a BC loop, BC weighting, basically, which is not good. So the system is really making progress indefinitely, but it's making progress that's not very useful, right? And definitely you want to really distinguish yourself between Livelock and deadlock. They are very different. They're both locking, but in different way, two different extremes. And the way to, also you want to make sure you understand invariance versus variance, right? By using the plot, okay? So this part is pretty accurate for the invariance, but for the variance, you want to look at what we just did before the break over here. So what you want to pay attention to will be, whenever you got any occurrence of the old events, like MLL and MLN, it's going to either increase the variant value or it's going to keep it the same. On the other hand, the idea about variance is to characterize the number of interleaving you can have for the new events. So that's why every time after a particular occurrence of the new events, you're going to see some strict decreasing trend for the value for the variance, right? So these are the kind of stuff you want to really remember, okay? And feel free to put that on your data sheets. That's absolutely fine. It's completely up to you. Okay, and then let's now talk about how we can formulate the variance into our proof obligation tool set. Okay? And I'll get to this page in just one moment. But let's take a look at the slides. Okay, so there are two proof obligations. One would be the variance should really stay non-negative. So that means the variance should always be on or above the 0. Right? That's number one. To really formulate it, it's not difficult. You just say this. Okay, I'll go over this with you very soon. But that's basically say we want to prove that the variant expression is a natural number. Okay? And then, you guys can read the bullet point, right? That's everything has been said already before the break. And the second one there is a little bit trickier. We want to say something like this. Let me show you what it looks like. It looks like this, but let's take a look. This one might need a little bit more visualization. Okay, so the first one here is to say the variance must be a natural number. And the second one here is this. We have the variance evaluated at the pre-states. And then we have the same variance evaluated at the post-states, after the event transition, of course. And this one will be at the post-states. And we are saying that the post-state value for the variance should be strictly smaller than the pre-state value. Okay, let's now see how that can be visualized. Think about, let's say if I have, let's say currently my variance, let's say currently my variance value is actually over here. And then I want to have an occurrence of some new events, for example, some new events. That one there's guaranteed to really strictly decrease the value for the variance. Okay? So think about the value in the pre-states is like a V and then CW, right? It's like this guy here. And the value after the event transition is going to be the same variance, but now also constant, but you have to factor in the effects of the event transition. Right? If you remember, F is about the concrete event transition. Okay? I'll just put W prime here. Okay? And that will just correspond to the trend that we observe in the plot before. Okay? Over here. You can see here, here, and here, right? Etc. All right, so this invariant here is about this. This proof obligation is about this. And this proof obligation here is really about your invariance should always be lower bounded by the 0. Okay? The variance should always be larger than or equal to 0. Or alternatively, it's a natural number. Okay? So these are the two things we want to prove. But what can we assume as the hypotheses? We can assume the axiom, the abstract invariance, all the concrete invariance, and also the guard of the new events. Okay? Well, sorry, the guard of the concrete events. Let me write it down. And then we'll see how to formulate it. And luckily, for these two proofs, usually they are not complicated. So I already got a solution on the slides. You can look at that, but I'm going to help you formulate them first. Okay? So these are, let me see this. Let's say axiom, and then we got abstract invariance, we got concrete invariance, and also we got concrete guard of the events. Okay, why don't we try the first one? And let's say the events we're considering is ILN. Okay? And for this one here, okay, I'll give you, what about axiom? It's going to be D, natural number, and also D larger than 0. Right? I just don't have the model here. I don't have space, but you can definitely look it up in the constant, in the context. And then What about abstract invariance? We actually got n should be a natural number, and also n less than or equal to d. So that's the abstract invariance. What about concrete invariance? We got 5 of them. Okay, so a is a natural number, b is a natural number, c is a natural number, and also a plus b plus c equals n, and also a equals 0 or c equals 0. Okay, and finally, for I of n, the guard should be a larger than 0. Okay, sorry, I'm just going to put it here. Okay, so these are all the hypotheses. Okay, and then everything here should really entail the goal. And that one there, what should that be? Well, here you can see we got basically 2 times a plus b. That's a variant, right? And we're going to say 2 times a plus b is a natural number. That's what you want to prove. It should be always the case. Yeah, Sarah. Okay, it's okay? All right, no problem. Yes, Ednan. Oh, so yeah, so this one here, yes. So now we are trying to formulate this particular proof obligation for the variant for our M1. So that's why I'm putting 2a plus b over here. So we need a rationale for this proof obligation. Oh, it's a very good question. Okay. Well, let's say this. If I really ask you to say, given this model here, come up with the variant expression, right? If I really do that. In that case, you have to basically, the only hint you have is you have to find some kind of combination of the constants and also the concrete variable ABC, and try to see how you can come up with some expression such that after every O event's occurrence, it's going to either increase it or keep it the same. And after every every new event's occurrence, it's going to decrease its value. Coming up with the variance is very difficult. I agree. So I would say the more likely question I will ask you is like this. I might say, given this variant over here, you want to formulate these two and then prove them. Or I give you, for example, let's say, exercise for you, which I forgot to mention. We just also mentioned in the slides. Let's say another variance, which is a plus b. Is it going to work? Right? In that way, you got to try some trace over here and also try to formulate a proof obligation to see if there's anything can be proved. Right? So I would say in the exam, I'm not saying I'm not going to do that, but it's more likely I will ask you to actually, given the variance, justify whether it can be used to prove it. But I would say, admittedly, variant coming up with it is very difficult, much more difficult than invariance. Yeah, I might just be nice to you guys for the exam. We'll see. Okay, but just make sure you get over-prepared rather than under-prepared. Right? Okay, that's good. And let's now. Okay, so hopefully you're okay with this, and that's the one you want to prove. And you can see the solution on the slides. What about this one? Okay, this one, let's make sure we do it. And you can see basically, this part here is just the same as this part, right? Exactly the same. So I'm just going to copy them. Okay, may not be very perfect. Give me a moment. There we go. Okay, and then let me put it over here. So that's the same hypotheses I can use. But now what I want to figure out is the goal, which is over here. Okay? And we do what we did earlier. Let's say there's got to be something here I want to do. I'll put a star. And we can come up with some intermediate version first. Right? Pre-states, we got some less than here. pre-state value for the variance would just be 2a plus b. Okay? And then the post-states will be 2 times a prime plus b prime. And what should a prime be? What should b prime be? You have to look up ILN. If you go back to ILN, a should be a minus 1. B should become b plus 1. So what's going to happen is this will be a minus 1, b plus 1, right? These two. So what you will get is, over here, write it down, 2 times a minus 1 plus b plus 1, strictly less than 2 times a plus b. And to formulate it, you don't really need to simplify it. That's okay. And so when you actually want to prove this sequence here, you can first apply arithmetic, ARI, to simplify it. That's okay. Okay? And guys, usually the variance proof are not really difficult. Usually they're more straightforward than invariant proof. So if you really run into some sequence that's unprovable, that means either the model is wrong, in which case you got to fix it, or the variant itself is wrong. Okay? Either way. Okay, any question? Yes, Sarah. You mean the goal over there? Yeah, absolutely. So for the exam, if you simply leave the goal like this, it's absolutely okay. And if you want to simplify it, that's okay too. But I would say save yourself some time. You will, if the question is only to formulate the sequence, you don't need to simplify it. Mm-hmm. Yeah. Okay, are we good? Okay, yes, please. That's not the, you mean just to show that it's larger than? Larger than or equal to show that it's wrong. But typically speaking, yeah, we'll attempt to try to prove this one here. If somehow that's unprovable, maybe go from there, you can try to argue. There might be some scenario where you simply got larger than or equal to. That's the way to show it. But first of all, you have to show that this is unprovable first. And then from there, you show this certain scenario or combination of the variables that's going to make it larger than or equal to. Yeah. So guys, the question is, if let's say if you're given, for example, let's say this alternative variance over here, how do you show that it's wrong? The correct answer should be, you should really formulate this one here and this one here for all the events first. And then to see which one is unprovable. And then from there, you can justify, just say, that's not the right variance. Okay, yeah, think about it. I know there's only one thing we'll talk about today, variance, but it's really worth our time. That was tricky, so that's why we need some time to think about it. Okay, any question? We good? Yes, Ryan. Oh, okay. So, yeah, so somehow I didn't really have that question here. So, how many? For example, net. Okay? The answer will be, it should be the number of concrete events, including the old and the new. Right? Because in order for the variance to really maintain a natural number, it's not just for the new events, but also for the old events as well. They should always stay above. Okay? And similarly for the variant decreasing proof obligation as well. Okay? Just all the concrete events. The number of concrete, which will be old plus new events, multiplied by the just one. Well, actually, that's good. Because every one of them, you want to make sure you prove about the net by replacing the concrete guard accordingly. And similarly for this. Okay. We've got about 5 minutes. How about this? I will definitely start you fresh for relative deadlock freedom next time. But why don't I just use the 5 minutes to talk about the next set of inference rules, which we'll need to prove relative data freedom. We just need 5 minutes. Okay, why don't we do that? So what I will do is, I'm going to move them right over here. All right, so these are the new 3 rules that you guys have to know. And somehow written test number 2 only covered the first set, right? Just make sure for the exam, you have to know everything we covered, okay, for the exam. And how about these 3? Let's understand them first. Okay, I will only use about up to 5 minutes, okay? So this one is saying, if the OR appears to the right of the turnstile, right? So you can think about the OR is appearing to the right of the turnstile. So this is the OR, right? If I have some disjunctive goal, in that way, I will be able to choose one of them, for example, P, and then move that as a hypothesis. And in that way, I can make it just not P. Let me say that again. If you have a goal that happens to be a disjunction, in that way, you can move the left-hand side to the hypothesis with its negation. And your favorite question, how do we justify this? Right? I will give you guys some reference if you're interested, but in order to justify this, this is what you have to do. Okay, this is what you have to prove. You want to prove that H implies P or Q. You can actually show the equivalence, actually. Is equivalent to, or if and only if, doesn't matter. H and not P implies Q. So think about this guy here is over here, right? Turnstile is like an implication, right? H implies P or Q. That should be equivalent to H and not P implies Q. By using some rules that we actually discussed in the review lecture, you will be able to prove this. It's actually quite straightforward. But the proof itself, I'll leave it as optional for you. If you really want to find out why, this will be your rule. What you should really know is having some disjunctive goal. You can move the left onto the right, onto the left-hand side of the turnstile and negate it. Can we move Q into here? According to the rule, you cannot, but you can easily, by doing arithmetic, you can say P or Q is actually Q or P. In that way, you can use the rule to move the Q into not Q. Okay? You can easily do that. Yes, Sarah. Okay, good question here. Good question. So let's look at that. So let's say ORR1. So here we got H, let's say P or Q. Now ORR1 tells me in order to prove this, it would be sufficient to prove just the left-hand side. Okay, if you now consider, okay, let's say this guy here. This one is saying, I don't really want to worry about Q anymore. I will simply just try to prove P. And I will do R2 if I just want to prove Q without worrying about P. Right? And now this one here, keep both P and Q. And then it's trying to move the P, which used to be the goal, as the new hypothesis, but with negated. That's the difference. Which one should you use? Again, trials and errors. Mm-hmm. So whenever you see like a disjunctive goal, now you got different possibility. Either you can move one of them into negated hypothesis, or you can simply use ORR1 or R2 to try, right? Okay, good, no problem. Okay, and I promise I'm going to finish in time. How about I'll stop here, and I'll take one question here before I let you guys go. Yes, go ahead. Yes, you have to. Okay, so guys, just one more. So, okay, I'll just, let's say here. Let's say here, if I got H, and then I got P or Q. In that way, I can say by arithmetic, I can turn this into H and then Q or P. In that case, I can apply the OR R. That one there is going to be H and not Q, and then P. Okay? That's how I can do it. Okay, thank you so much. And then if you got trouble with lab number 3, TA will be there 1 p.m. today. Okay, otherwise, my office hour. Take care. I'll see you on Thursday.